All right, it is a dreary Saturday night. It's drizzly and a little bit chilly, so what better thing to do on a dreary Saturday night than some algebra, right? So let's just get started with Unit 5, Lesson 2. This is on multiplying and dividing radicals. Now, I have taught adding and subtracting first. Some years I'll teach adding and subtracting first. Some years I'll teach multiplying and dividing first. There's arguments to be made for either one. But this year, we're going to start with multiplying and dividing our radicals. So without further ado, let's get going. So there's a key idea, and remember that we want to focus on our key ideas. Now, I did title this slide multiplying radicals / roots because you might hear it multiplying roots, okay? And we want to make sure that we know all of the vocabulary that might get thrown at us with that. So as always, we want to focus on those key ideas because the key ideas are the things that don't change even when you change what a problem might look like. So the key idea in multiplying radicals is this. If you have the square root of a times the square root of b, that is equal to the square root of a times b. In other words, you can take that multiplication and you can move the whole multiplication under the radical. Now, why you can do that has to actually do with exponents, which is going to come later in this unit. Now, I know I've talked to some of the other teachers. Some teachers will start this unit with the exponents. So they'll teach you the connection between the roots and the exponents at the outset. Again, there's like a lot of different ways you could approach this, but we're just going to approach this with this key idea that the square root of a times the square root of b is equal to the square root of a times b, and essentially you can multiply the numbers under the radical. Now, we've actually used this property or this key idea in the other direction when we've had, say, simplifying a radical. So, for example, if you had like the square root of, I don't know, 18, we've like split it up into the square root of 9 times the square root of 2 and then broken it up. And right there is where we would use this property where except we're going in the other direction where we have them together under the radical and then we're splitting them up. So if this does look a little familiar to you, that's probably why. Now, this is the kind of little blurb that will be in math textbooks and people just kind of overlook it. This key idea only works if A and B are not both negative. Okay, so they can't both be negative. It's okay if one of them is negative, and it's okay if neither of them are negative, but they cannot both be negative, and we'll take a look at that in a little bit. So I have here 3 examples, and we're just going to see how this works. So if you have the square root of 2 times the square root of 5, that would be equal to the square root of 2 times 5, which of course is the square root of 10. Now, most people are just going to skip right to the square root of 10. Okay, now typically when I'm first presenting this and I really want to emphasize that key idea, I won't skip that step because I'm trying to emphasize the key idea. But yes, practically speaking, like you guys can do 2 times 5 in your head. You don't need to write it as a separate step. Okay. Second one, this one's going to have a little bit of a twist to it. So we have the square root of 2 times the square root of 6. So as we just went through, that would be equal to the square root of 2 times 6, and 2 times 6 is 12. Now, you might be tempted to stop right here, except general practice in math says that you simplify radicals. So this is going to tie us into the previous lesson. If you are, for some reason, watching this lesson without having gotten the previous lesson, please go back and watch the previous lesson first. Order matters. Pillage, then burn. Okay, so when you're looking at the square root of 12, that can be simplified. And what we're going to do is essentially reverse this process except with different factors. So now I'm going to factor the 12 into 4 times 3 because I can take the square root of 4. The square root of 4 is 2, and so that will simplify into 2 root 3. Now, there are other ways to do that. You can, of course, go do prime factorization like we discussed in the previous lesson, if that's better for you for getting that 2 root 3, okay? But when you are multiplying them together, most of the time the directions are going to say like do the operation and write your answer in simplified form. So we want to know what we mean by that and what that process would look like. Not everything is going to be simplifiable, as you can see from the first example, but if it is simplifiable, you need to simplify it. Third one is the square root of 3 times the square root of 3. Now there's a couple of ways that you can think your way through this. So one way that you could think your way through it is by using that key idea. So this would be the square root of 3 times 3, which is 9, and the square root of 9 is 3. Okay? Or you could do the prime factorization and say, okay, this is a square root. And so if it's a square root, I'm looking for groups of 2, and there's the group of 2, and it's a 3. Now, the other way you could think about this is to multiply something by itself, the square root of 3 times the square root of 3. That is the very definition of squaring. And if you think back to the previous lesson, we talked about how squaring and square rooting undo each other. And so if you've got something and you take the square root and then you immediately square it, that is going to undo itself and you're going to end up at the 3. So both of those are valid ways to think through how to do the problem. It's one problem, so you should end up with the same answer no matter how you're thinking about it. But it's nice to just illustrate there's more than one way for you to process what's happening in that problem. Let's be curious. What happens if they are both negative? So we want to approach math with a little bit of curiosity. What happens if you get that statement like this only works if they're not both negative, and then you can see, okay, I get how this principle works, then you might want to ask yourself, okay, well, what happens if they are both negative? Why doesn't it work? And you want to ask those questions, like stoke that curiosity. Sometimes you can stumble across some really interesting answers there. So this is an example, and what we're going to show with this is that this property doesn't work with when they're both negative. Now, this is what's called a counter example. So if you were to say, the key idea is the square root of a times square root of b equals square root of a times b. And it's not always true. All you need to do is show one example when it's not true. And so we're going to show that it doesn't work when they're both negative. So it's not quite the same as a proof. A proof is showing that it always works. A counterexample is a way that you show something is false or that it doesn't work. As long as you can come up with a counterexample, that's usually the simpler thing to do. So if I were to take a look at the square root of -4, we're going to use some of our information from a previous unit. We're going to say that's equal to the square root of 4 times -1. Okay, and so we've got 2 of those there. And of course, this we can use that key property there, which is fine because they're not both negative in this case. So we have a +4 and a -1. Square root of 4 is 2, and the square root of -1 is I. So we end up with 2I times 2I. So far, so good. Remember, multiplication is commutative, so you can change the order on that. 2 times 2 is 4, and I times I is I squared. But if you think back, it's actually a couple units now. What does I squared equal? Well, I squared is equal to -1, and we get -4. So the square root of -4 times the square root of -4 is -4, which is fine, okay? In fact, you can get there if you do this idea of the square root of -4 times itself is squaring it, and then the squaring undoes the square rooting, giving you the -4, okay? Now, over here, the square root of -4 times -4, well, -4 times -4 is 16, and the square root of 16 is 4. And so if I kind of follow that all the way down, we had like a lot of steps in there. When I do this in class, I'll try to clean it up. essentially one side is equal to -4 and the other side is equal to +4. Therefore, they aren't equal to each other. So if both of the numbers are negative, then you cannot put them both under the square root together and multiply them. You can go through the process of simplifying each one individually. Okay, that would be fine. And you'll get your eyes out at the end. But if you try multiplying them together, essentially you lose the negativeness of it, and you end up losing, like you lose the I squared, and then you lose the negative. Okay, so that's why it doesn't work if they are both negative. So you can also multiply binomials. Remember your vocabulary here. Bi means two. Nomial has to do with numerical expressions and stuff. And so what we have here is a binomial times another binomial. So there's multiplication happening in between, and this is a binomial because it is 2 plus the square root of 3. So it has these two terms there. Now you can do this with any number of methods. I am going to use area model because that is what we've been using in class this year. So we have, okay, and now we'll just take each box separately. So 4 times 2 is 8. Now you get to 4 times root 3, you might think, you can't do much with that. That is actually just 4 root 3. So essentially you can't do anything with it. 4 times root 3 has to stay as 4 times root 3. And I do want to point out briefly that that is multiplication right there. Okay. So that's 4 times root 3. Basically you can't do anything with it. The next box, upper right, 2 times root 5. And you're stuck. It's just 2 times root 5. Now you would read that out loud, 2 root 5 or 2 radical 5, 2 square root 5, but it is multiplication. And then down in our lower right, we have the square root of 3 times the square root of 5, which we just established would be equal to the square root of 3 times 5, which is the square root of 15. And as is always the case with the area model, you do need to add them up because what we're trying to do is get the area. And so once we do the base times the height, we need the whole thing. So we have 8 plus 2 root 5 plus 4 root 3 plus root 15. And for now, that's where you need to leave it. Now, there are some situations where you might be able to simplify those radicals and you could go further, but we haven't talked about adding radicals yet. So try not to slam you with that in this video because that would be kind of mean, but also I don't vouch for myself. So, all right. So that's what it looks like to multiply your binomials. So on the next slide, we do have 6 practice problems, and if you're watching from home or using this video to review, definitely pause the video. Watching me do it, listening to me explain through a problem is not the same as you trying to do it. And of course, on your test, on your SAT, on your end of course exams, college entrance exams, you're going to have to be able to do them. So risk-free, pause the video, try to do the problems out, and then unpause it, and we'll talk about them. Okay, so hopefully you did that. And what I will do is I'll work the problems out on the blank part of the screen for a little bit, and then when I kind of run out of space, I'll erase them. So make sure that you're pausing as needed if you need to make corrections to your own work. So for the first one, we have the square root of 3 times the square root of 5, which would be equal to the square root of 3 times 5. We just did this in the other problem we just did. Square root of 15. Okay, everybody can do that. That's not beyond like the scope. The reason of this course or anything, the reason why students get this wrong is because they don't prepare, they don't study, they end up getting multiplication confused with some of the other operations and they do something else. Okay, so don't let that be you. Make sure you get enough practice. Next one is the square root of 6 times the square root of 3. And this time I'm going to go ahead and skip that middle step. I know I'm just going to do 6 times 3, which is 18. Now, before we can stop with the problem and say, oh, that's great, I'm done, we do need to consider the possibility that this is simplifiable. And in this case, it is. So the square root of 18 does factor into 9 times 2. Square root of 9 times 2, and the square root of 9 is 3 root 2. So if you got the square root of 18 but you didn't simplify it, pause the video and supplement your notes. Don't leave your notes or your practice work with an error in it. Make sure that you're taking the time to correct it, because that act of correcting and noticing your error will help the concept stick in your head better, so that you remember it better next time. Number 3, we have the square root of 4 times the square root of 4. That would give us the square root of 4 times 4, which is 16, which is 4. And you actually can go straight to the answer there. I would not expect you to have to write the square root of 16. Okay, so there's the first 3. That took us about 2.5 minutes, not even. And I'm going to erase this and make some room for those pesky binomials. So okay. So we have 3 plus root 2 times 4 minus root 5. So setting up our area model, we have 3 root 2 and then 4 minus root 5. And so each of these, of course, becomes its own separate problem. 3 times 4 is 12. 4 times the square root of 2 is just 4 times the square root of 2. That you have to write it like that. That's the only thing you can do. Upper right, we have 3 times negative root 5. Well, a positive times a negative will give us negative, and then it's just 3 root 5. And then we have a root 2 times a negative root 5. So positive times a negative gives me negative, and 2 times 5 is 10. So my answer would be 12 plus 4 root 2 minus 3 root 5 minus root 10. Now, let's say you have these two switched. That's totally fine. Just make sure the 4 root 2 is positive and the 3 root 5 is negative, okay? But you might have like written them down kind of going in this order. But just think about what addition is, okay, and what we're doing here. So if you have like 3 plus 2, that's the same as writing 2 plus 3, okay? That's called commutativity, which means that you can just switch the order. Just make sure that if you did that, that you changed the sign with it so that you're adding and subtracting one along with it. Okay, now if you take a look at number 5 should look different. Number 5 are conjugates. So that's when we have the same terms and one of them is a plus and one of them is a minus. And we know that conjugates are really important. That word keeps coming back up over and over and over again. And so we'd maybe be expecting this to do something a little different. So if you did think it through, you kind of think it through right now. Or maybe look at your answer and say, it did do something weird. Or maybe not weird. Like once you see it, you should expect it, okay. Okay, let's throw some stuff in here. 2 times 2 is 4. 2 times root 5 is 2 root 5. That's all you can do with it. Then we have 2 times negative root 5. So a positive times a negative is a negative. And then we just have the 2 root 5. And then we have positive root 5 times negative root 5. So a positive times a negative gives me a negative. And then root 5 times root 5, okay, is root 25, which is just 5. Now, when you go to write this out, you should notice something that happens with conjugates. And you should notice that your middle terms cancel out. So if you have plus 2 root 5 and then minus 2 root 5, those cancel out and you are left with 4 minus 5, which is -1. You can also, I don't have Desmos pulled up in this particular slide, but you can like pull Desmos up and verify that. Desmos won't give you the answers with the square roots in them, so it'll revert everything over to a decimal. But so you can't, like, it's got limits to what you can check with it, but this one, when you come up with a -1, you could definitely check that. So I do want you to notice that when you multiply the conjugates, the product does not have the square root in it anymore. All right, and moving on to our last one. And this one should be interesting. I like fun problems. We have 4 root 2x. Oh, shoot, that should be a times sign. Times sign. If that bothered you, now you know why it bothered you. I have it on my page here. It's not that you can see it, but it is written correctly on my page there. I just typed it wrong. Note to self, fix that before you teach this in class. Okay, so before, feel free to have a moment of panic with this, especially if you had the wrong operator in between. Really sorry. Okay, so to have a moment of panic, but then you want to think to yourself, math is consistent. The principles that work in one situation, they work everywhere. So we're going to do the best we can with this. Now, remember what I said about these being multiplication. Okay, so this is 4 times the square root of 2x, and this is 5 times the square root of 6xy squared, okay? Now, multiplication, like addition, is commutative, which means you can multiply them in any order. So my first step here, which is really optional, I am doing this just so you can see why this works. I'm going to switch my 2 middle expressions here. So instead of root 2x times 5, I'm going to do 5 times root 2x, okay? So 4 times 5 times root 2x. And that did absolutely nothing algebraically, but it did visually put my similar things together. So I have the 4 times 5 together, so I have my stuff that's not under the square root together, and then I have my stuff that is under the square root together. But algebraically, I haven't done anything. But I can maybe make some headway here. So like 4 times 5 is 20. And now that you have the 2 square roots next to each other, now you think, okay, well, I should be able to just multiply the radicands there. So that would give me the square root of. And we're just going to multiply this together. So 2 times 6 is 12. X times x is x squared, and then we have the y squared. And that looks just like a problem from the previous lesson. So I'm going to go ahead and do my prime factorization on this. 12 factors into, well, we could just do the 2 times 6, and then 6 is 2 times 3. And then we have x times x and y times y. And because it is a square root, we're going to be looking for groups of 2. There's 1, there's 1, and there's 1. So those are going to come out. So we're going to have 2, and x, and y. And what are we left with? The 3 is still going to be left underneath there. And then 2 times 20 gives me 40. Now, is it true that that does not look like any of the example problems I did? Yes, it is true. That does not look like any of the example problems. But it's also true that this particular problem does not draw on any piece of information that you don't already know. So you already know about commutativity. Okay, you know that you can multiply things in any order. You already know how to multiply 2 radicals. You already know like that 2 times 6 is 12 and x times x is x squared. you already know from our previous lesson how to go about simplifying something that looks like this, and you already know that 20 times 2 is going to give you the 40. So I do want you to pause and think about that, especially if you got stuck on this, or worse, you just didn't try to do it because it looked really, really unfamiliar to you. Okay, you don't have to be shown a specific example that always looks exactly like what you're going to have to do. If you know the key ideas, if you know how the math works, then you know it's consistent. It's always going to work that way. You don't have to freak out about it. Okay, you just like move ahead and say, well, what do I know works for the stuff that I have in front of me? And don't be afraid, even if you got it wrong. Okay, if you got it wrong, it's a practice problem. So pause the video, make a correction, and move on. All right, now dividing radicals and roots, the same principle applies, which should surprise exactly no one because math is consistent. Actually, the reason why the same principle applies is because there's no such thing as division. Division is only ever multiplication by the reciprocal, but we'll still list it out. So the key idea is this. If you have the square root of a divided by the square root of b, that could be written as the square root of a over b. And again, the reason for that has to do with the fact that your division is just multiplication by the reciprocal. Now, what might that look like in a particular problem? Well, we have the square root of 8 over the square root of 2. So that could be written as the square root of 8 over 2. 8 over 2 is 4, and the square root of 4 is 2. That is not the only way to do that problem. So because I can, and it's a dreary Saturday night that is now gotten very dark outside, we could also do this a different way. We know that the square root of 8, we know that 8 is 2 times 2 times 2. And we know that when it's a square root, we would be looking for groups of 2. So that would be 2 root 2. And anything divided by itself is 1, leaving you with a 2. It's the same problem with the same directions. So you should get the same answer, but it is a different way of doing it. And again, it's like just good to know that like there's more than one way to do these. So if you're looking at something and you see a different way to do it, that's totally fine. You can always ask in class. Sometimes students will stumble across something that's a legitimate coincidence that something works, but a lot of times you guys see those patterns and they are connected, and you can develop a way of solving these problems that really works for you. Now, this one, I'm going to grumble a little bit, okay? You may need a process, and this process is called rationalizing the denominator. Okay, it is called rationalizing the denominator. Now, outside of math class, if somebody is trying to rationalize something, it usually means they did something wrong and they're trying to explain it in a way that makes it make sense. In math, when we're talking about rationalizing, we're talking about taking something that is irrational and making it rational. In this case, the denominator. So if I look at the denominator, see that square root of 2? That square root of 2 is irrational. And so what I am trying to do when I rationalize the denominator is I am trying to rewrite my fraction so that the square root is not, so that the square root is not in the denominator. So that the square root, there we go. So that the square root is not in the denominator. You're not really doing any division here per se. You're just rewriting it. It is a math rule because basically like an irrational number cannot be written as a fraction. And so it's undefined or impossible to write in the denominator of a fraction something that cannot be written as a fraction. It like violates our definitions. The engineer in me says I don't care. I'm just going to change it to a decimal anyway, and then I'm going to move on with my life because engineers would use decimals most of the time. But mathematicians, they like to follow their rules. So if you are in a science class or a math class, you can follow the math rules. Science class or an engineering class. Sorry, I think I said that wrong. If you're in a science class or an engineering class, you would use the math rules that are set out by that discipline. But if you are in a math class, you have to use the math rules that are set out by mathematicians. So this is for a math class. So we have to do it. Now, what we're going to do to get there is we're going to leverage the behavior of those conjugates. So if you think back to that example problem, when we multiplied by a conjugate, there was no square root left. Okay, the square roots in the middle ended up canceling out, and the one at the end, we ended up squaring the square root, which got rid of it. Now, remember what we're trying to do here. We want to get the square root out of the denominator. So what I am going to do is multiply by the conjugate of the denominator, because that's where we're trying to get rid of the square root. Now, if this is a fraction, so I cannot just multiply a denominator, okay? If you have half of a pizza and you just multiply the bottom of the bottom, okay, an eighth of a pizza is not the same as half a pizza, okay? It doesn't work that way. If you have a fraction and you multiply the bottom by something, you have to multiply the top by the same thing, okay? So I can do 4 over 8. That's the same as half a pizza, okay? 1/2. But so whatever you multiply the denominator by, you also have to multiply the numerator by the same thing. And so this is what it ends up looking like. Now, pretty much from here on out, you just need to do the work to get those things multiplied. I'm not going to tell you it's beautiful or wonderful or fun. It's not. It's a pain in the neck. But you take it one step at a time and you just get done what you need to get done. So for that first multiplication, I'm going to have 3 root 5 times 2 root 2, or 2 times 3 plus root 5 times 2 plus root 2. 3 times 2 is 6. The good news is that I can't do anything with that, so that's 2 root 5. This will be 3 root 2, and then the square root of 2 times the square root of 5 we've done already today. That is root 10. So my numerator is going to be 6 plus 2 root 5 plus 3 root 2 plus root 10 over something. Here we go. So this is 2 minus root 2 times 2 plus root 2. 2 times 2 is 4. Now, if you want to, you know that the middle pieces are going to cancel out anyway. So if you don't want to do them, that's fine by me. So this will be negative 2 root 2, and this will be positive 2 root 2, which we know because they're conjugates are going to end up canceling each other out. Then we'll have negative, the square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. And so this ends up being 4 minus 2, which is 2. So my denominator is 2. Now, in some problems, you can go further than this. Like you might have a common factor somewhere that you have to factor out. I will be super happy if we can just get this, just get it as far as you can, and I'll try to avoid anything that is unnecessarily complicated when it comes to rationalizing the denominator. Now, there are some other kinds of problems where you might need to rationalize denominators that are easier than this, where you wouldn't necessarily need the conjugate. So for instance, if you saw something like this, like 1 over the square root of 2, you could just do this, the square root of 2 over the square root of 2, because that's still equal to 1, okay? It's still multiplying everything by 1, but is a lot less complicated. And you might remember that from geometry when you were dealing with special right triangles. Maybe you remember that, but you did have to do it in geometry. Okay, a couple of practice problems. So go ahead, pause the video. Don't gyp yourself with your practice problems. Make sure that you're giving them a fair shake. And then when you've done your best, go ahead, unpause the video, and we'll go over them together. Okay, hopefully the first one did not take you any time. So the first one, we'd have the square root of 6 over the square root of 2, and that would be the square root of 6 over 2, which is equal to the square root of 3. Okay, now you could also do that this way, and I really don't know how photomath would do it, but you could do what I said on the previous slide and multiply that ratio by the square root of 2 over the square root of 2. That'll give you the square root of 12 over 2. And if you remember from way back at the beginning of this lesson, when we had the square root of 12, the square root of 12 simplified into 2 root 3, and then your 2's would cancel out. Okay? So you could do it that way as well. I wouldn't recommend it unless I had no choice, but it does work. Now, for the second one here, we do need to go through that process called rationalizing the denominator. Remember, the denominator is the thing that we're trying to rationalize, and so it's the conjugate of the denominator that we need to use. So if the denominator is 2 plus root 3, we would use 2 minus root 3. Whatever that middle sign is, you're going to flip it. And then because of fractions, you need to make sure you multiply the numerator by the same thing. So let's do some scratch work. We have 1 plus root 2 times 2 minus root 3. 1 times 2 is 2. 2 times root 2 is 2 root 2. This will be negative root 3 or negative 1 root 3, and this will be negative root 6. So my numerator is 2 plus 2 root 2 minus root 3 minus root 6 all over. Bottom one should be nicer. Okay, so 2 root 3 and then 2 minus root 3. And we have 2 times 2 is 4. This will be positive 2 root 3. This will be negative 2 root 3. Aren't conjugates awesome? Positive times a negative is a negative, and then the square root of 3 times the square root of 3 is the square root of 9, and the square root of 9 is 3. And so we have 4 minus 3, which is 1. And then for most of us, you don't need to write 1 like over 1. It's not wrong, but dividing by 1 doesn't do anything. And so there's no reason to write the denominator there. Okay? If I end up, we're like weeks away from a test on this, but if I end up putting something like this on a test, it'll be something like this that comes out fairly nice, because what I'm looking for is whether or not you understand what that procedure is, and then how to execute it, not whether or not you can get some like crazy messy thing that involves more simplification and so forth. Okay. So we'll try to keep that as clean as possible. As always with the practice problems, if you got something wrong, it's fine. It's a practice problem. But do pause the video and make those written corrections to your work in order to help the concept stick better. And because math is consistent, because key ideas, key concepts, operators, how they work, they stay the same across all of our algebra, and we want to make sure that we're focusing on the right things. Everything that works for square roots also works for other types of roots. So for example, a cube root. So even though all of the examples that we did in this lesson were square roots, and the reason I do that is because the vast majority of all of the roots that you will ever see in your life are going to be square roots. So that is what we want to emphasize and focus on. But none of these ideas change just because you have another type of root. So if you had the cube root of 2 times the cube root of 4, that would be the cube root of cube root. Hang on, I just don't want to leave it like that. Cube root of 2 times 4, which would be the cube root of 8, which would be 2. And if you're like, I don't remember that, how do you know that? 8 factors into 2 times 2 times 2, and because it's a cube root, you're looking for a group of 3, and there's your 2. Okay, so that was like a little review from the last lesson. So all of that still works. Every year up until this year, unless I change, kind of what I do, I've put a problem like this on the unit test and students get it wrong because I actually don't know why. So everything that works for square roots works for cube roots. Don't forget one lesson in favor of another, okay? And lastly, your homework is going to be, at least the year that I'm recording this, which is January of 2023 when I'm recording this. Your homework is in a packet. If you're watching this for another teacher, obviously your homework is going to be something else. Or for me, for a different year, just make sure you're paying attention to what I hand or say and do in class. I apologize for the couple of typos that were in there, especially that one on the practice problem. I do need to make sure I fix that. And you know how to reach me if you have any questions.